Good morning, all. So, welcome to this course, Analog Circuits. So, previous session we started off with oscillators, right? So, what is it, oscillators and where it is used, and different other types of wave shaping circuits, multivibrators, and all we have discussed. Okay. So, today we'll continue the discussion. We'll give you a brief overview on basic principles and the criteria for oscillation, and then we'll start with the phase shift oscillator discussion. Okay. So what is meant by an oscillator? So oscillator is an amplifier along with an frequency selective network forming an positive feedback loop is called an oscillator. Okay, so this is same like a block diagram you have seen in a general block diagram of a control system, right? So where you had this as a G, right? And this is the feedback network we call there as H. Okay, and instead we had the summing points with plus minus sign here, R of S, C of S. So same diagram you are going to see here, right? But this is not that, but it is a amplifier with frequency selective feedback loop, but the expression will come same way. Okay, because the mathematics will not change for any subject. So when you do the simplification or if you do the derivation of this, okay, so it's output, okay, x naught by xs or whatever, so or gain we call it here, right? So in control system we call it as transfer function, nothing but output by input. The same thing here in the amplifier circuits, it is output by input is nothing but the gain. So if you are measuring with voltage, it is voltage gain. With current is called current gain. Okay, so same way, so the overall gain of this block diagram is called as x naught by xs, nothing but the same formula how you are getting G by 1 plus GH, because here minus sign used to be there in control system, but now for oscillator we are using positive feedback, that's why it is plus is there. Because of that in the denominator will come minus, only that is the difference. Okay, so that's why no derivation is there, directly I will give you the equation. It is A divided by 1 minus A into beta. Okay, so A is nothing but the amplifier gain and beta is nothing but the frequency selective network factor. Okay, so here xs is the source signal, x naught is the output signal, and xf is the feedback signal. Okay, so this is what we have discussed. So we'll continue the discussion. Okay, so how the equation looks like, and based on that the criteria we will set. So here the feedback signal xf is summed up with the input, okay, the positive sign. Okay, so that's why the gain with feedback is given by, so okay, so A of S, because again it is in S form only, so Laplace domain. Okay, so AF of S is equal to A of S by 1 minus A of S B of S, same like in control system you had G of S 1 plus G of S H of S, right? So generally we will not write this S term because it is understood that we are measuring in that domain. Okay, so A divided by 1 minus A beta, this is the gain you have to remember for oscillator circuit in general. Okay, the loop gain of the circuit in figure A is minus A into beta. The loop gain is nothing but only this term. Okay, so 1 minus or plus whatever is there, this is called as just loop gain. Okay, and this together we call it as overall loop gain or gain with feedback we call. Okay, so that's why this loop gain term will be used here for setting the criteria. However, for our purposes here, it is more convenient to drop the minus sign and define the loop gain L of S as. Loop gain will define or denote it as L of S, which is given as dropping the minus sign. It will remain is A of S into B of S. So normally it is taken as magnitude. When you take magnitude, minus sign will go automatically. Okay, so that is about the loop gain, and the characteristic equation thus becomes. So what is meant by characteristic equation in mathematics? So the denominator is equated to 0. Okay, so in the gain equation, if you equate the denominator equal to 0, so even next we are discussing now second order systems in control system. So we have the second order transfer function denominator, right? S square plus 2 zeta omega ns plus omega n square, right? So even that denominator, if we equate to 0, it is called as characteristic equation. Based on that, we will find out the stability factor. Okay, so that is next discussion we have. The same way, it is mathematics. Okay, so the denominator, if I equate to 0, so that we call it as the characteristic equation. So here denominator is A of S into beta of S. So that is denoted as L of S. That's why it is 1 minus L of S equal to 0. So these are some of the equations relating to the oscillator. Okay, I hope it is clear. So there is no much difficulty here. Okay, so now we'll define the oscillation criterion. Okay. Okay. So in the circuit, so you have to get a oscillation, right? Like sinusoidal wave automatically means. So there should be some parameters it should set, right? So if you have just switched on, it will not come, right? There are some criteria based on that only it will set. So for that, if at a specific frequency f naught, the loop gain a beta is equal to unity, it follows from equation that af will be infinite. So a divided by 1 minus a beta was there. If we take a beta equal to 1, then 1 minus 1 is 0 will come in the denominator. So it will come infinite. Okay. So if we make that assumption, that is at this frequency, the circuit will have a finite output for zero input signal. The meaning in another way it is saying is the circuit will have a finite output for zero input signal. So such a circuit is given and definition called as oscillator. Okay, so that only sets the criteria. So we'll see that in next slide. Thus, the condition for the feedback loop of figure A to provide sinusoidal oscillations of frequency omega naught is, okay, wherever S is there, I will substitute j omega. Okay, so you know that already S is nothing but a complex frequency domain. So it is having the real part along with imaginary part. Okay, so real part will not be there, so it will be 0. So only the imaginary part will be considering, because the sinusoidal wave we are taking in the upper one, right, j axis. So j omega will substitute when we are determining the frequency domain. Okay, so that omega I will substitute as omega naught. Okay, frequency fo. So L of j omega equal to a of j omega beta of j omega, this equal to 1 we will set. This is the criteria. That is at omega naught. That means this oscillation will happen at only that frequency. Okay, so not at other frequency. That's why that omega naught is specified. The phase of the loop gain should be 0 and the magnitude of the loop gain should be unity. That is the two criteria for oscillation. The magnitude of a beta should be equal to 1 and the angle, okay, the phase of the a beta, that is the multiplication, should be 0 degree or 360 degree. Okay, so 0 degree or 360 degree. That means what? You start from 0 degree, 90 degree. Okay, so 180 degree and you will come back to 360 degree means what? It is again 0 degree. Okay, so both are same. So this is known as Barkha-Hassan criteria. This is given by the person Barkha-Hassan. So he given this criteria. Okay, we are not going to say. So he has done the research on this and he put forth this condition a beta equal to 1 and angle should be 0. That's why it is called as Barkha-Hassan criteria. So very important this one, Barkha-Hassan criterion for oscillation. Okay, so maybe in basic electronics you had this criteria, I don't know. Okay, so but this is a very important 5 marks question earlier. Okay, but in this syllabus they have not put this introduction part, but as a necessity we have to tell this only, we have to continue. So that's why I took this. Okay, so Barkha-Hassan criterion we call. Note that for the circuit to oscillate at one frequency, the oscillation criteria should be satisfied only at one frequency. See here, so oscillation criteria, whatever we are saying, it should satisfy at that only frequency. Otherwise the resulting waveform will not be a simple sinusoid. So whatever I am saying, it may be going above the head. Okay, I understand that, because so this is a practical thing. So even in the laboratory and all, if you sit with CRO everything, and if you do this, you will see that oscillations generating and all. Okay, we have the oscillators experiments are there. Okay, so in AC lab, so get vaccinated and we'll start the online offline classes. Maybe labs also will start soon. Okay, so hope so. So then you will be clear with all these concepts, everything. Okay, so now at least try to give a imagination how it will be looks like. Okay, or you can search in YouTube such videos, oscillation and all. Finally, in oscillator circuit, stability of frequency is a very important criteria. So just setting the oscillation is not important. Okay, so even if you have taken some device in home, so you have taken a mobile phone, just it is on and it is working, not important. It should come long life, right? At least 1 year, 2 year, 3 year, right? It should give a better result. Same way, if you have set a oscillation, because of some reason it may go deviation, it may end off. Okay, so this should not happen. That is the stability, that is very important criteria. Okay, so as in same amplifier stability point we have told, right? Stability, so switching on the device is not important, keeping that stable, okay, or the oscillating Q point maintaining is important. Same way here, oscillation is important. Second way, It's a stability part. Okay, even in control system also you'll study like that. Okay, so transient, these things we are learning. So its stability part is the next aspect. Okay, the frequency stability of an oscillator is the definition is this ability of the oscillator circuit to provide constant frequency over a long time. So that is what called as stability. So it should provide constant frequency over a long time. What is constant frequency? See here, this is the one time clock cycle. It's reciprocal, we call it as frequency. This should be same uniform to next cycles also. So one will be giving some frequency, another no, then it is not called stable. Okay, so for that again criteria is that the ratio of change in phase to the change in frequency decides. Okay, so d theta by d omega. Theta is phase, omega is frequency. The ratio of change in phase to change in frequency decides the frequency stability of the oscillator. Okay, and this value should be very high to keep the high stability. Okay, the high value of indicates high frequency stability. So this is a brief introduction about the oscillation. Barkhasan criterion we have seen. What is meant by oscillator? Amplifier with frequency selective network forming a positive feedback loop generates sinusoidal oscillations. Okay, that is oscillator we call. So then Barkhasan criterion we have seen, that is magnitude of loop gain should be equal to 1. Loop gain is here defined as amplitude gain into beta factor. Okay, both multiplied and its magnitude is taken. Okay, minus sign is there, we will neglect, and its angle should be 0 degree. Okay, so based on this criterion only we will have different types of oscillators also, and that also we'll see. Okay, so some more points. An alternative approach to the study of oscillator. Okay, so this is one approach what we have done. So an alternative approach to the study of oscillator circuit consists of examining the circuit poles, which are the roots of the characteristic equation. I told you characteristic equation, right? 1 minus a into beta is equal to 0. 1 minus ls equal to 0. Equation 3 I shown you, right? So that equation, using that also you can do the analysis. Okay, so what is the criterion for oscillation? Okay, for the circuit to produce sustained oscillations at a frequency omega naught, the characteristic equation has to have the roots at s equal to plus or minus j omega naught. So if you equate the denominator equal to 0 and if you solve that, you should get the roots either at plus j omega and minus j omega. That means what is plus j omega? So this is the your axis, right? So this is the 0 origin. Okay, plus j omega means some value, so plus 1 I say. Okay, so it's exact same magnitude should be there on left side, means minus 1. This is the poles. So based on that poles only your waveforms will generate, right? So the poles are uniform. Okay, that it's uniform means it is giving sustained oscillations. So now it is giving at a 2. Okay, so omega here it is at 2 and here it is 1, means it is not uniform because it is not satisfying this one, right? The criteria plus or minus j omega. Okay, so that's why in this way also you can say the sustained oscillation criteria. Thus 1 minus a of s into beta of s should have a factor of the form s square plus omega naught square. Okay, so the characteristic equation should come in this form, then it can produce the sustained oscillations. Okay, so no need to much think about. So you know already poles, you have studied jet transforms in signals and system and all. I also told you in transfer function while discussing what is poles and zeros, and this we will be going much further in control system aspect, then you will understand that. Okay, so you need to remember just what is the criteria for sustained oscillations, Barkhasan criteria. Okay, something like that, and what is oscillator. Okay, so based on this introduction, we will be learning various types of oscillator circuits here. That is what they are in your syllabus. So one is called as, so here the oscillator types depends on your frequency selective network. Amplifier you have already designed, common source amplifier, common drain amplifier, common gate amplifier. Like that you have different configuration of amplifiers you have, and you know based on the circuit. Okay, so you can how to write the small signal equivalent model, do the analysis and write the final voltage gain, everything you know. That is about the amplifier aspect. So based on that we could not do classification. Okay, so what is the classification based on is here the feedback part, that is the frequency selective network I told you, no? So it should give 180-degree phase shift because amplifier is giving a 180-degree phase shift that we have learned in common source amplifier. So if you give a wave of positive negative like this, when you see its output waveform, it will be having a minus sign. You have seen minus gm into rd, something like that, right? Voltage gain, nothing but what, for positive cycle you will have a magnitude of negative, and positive you will have negative, you will have positive, like this. You will get a 180-degree phase shift between input and output. So that is the amplifier. Now what we have done, we have kept the amplifier in the upside, right? A, it is the giving 180-degree phase shift. So now you have to select a frequency selective network. It should nullify this 180-degree and it will give total phase shift as 0-degree. That is your Bhatkal criteria, right? It should be 0-degree or it comes back to 360-degree. So for that, whatever frequency selective network you will consider in the bottom, that is beta factor, so that should give another 180-degree phase shift. Okay, so to get that, we will form different combinations of circuits. Okay, so that only the classification we call. So one is called as RC phase shift oscillator, or phase shift oscillator we call. So here we will use the passive elements resistor and capacitor combinations in 3 sections. Okay, so each section of RC will give you 60-degree phase shift. So it's cascading of 3 RC will use, producing total 180-degree, which will get added with the amplifier 180-degree, and it will produce the 360-degree, which is nothing but 0-degree. Likewise, it will satisfy the criteria and it is able to generate oscillations. Okay, so that is the first type. So similarly, we have LC tuned oscillators. Okay, so here we will use inductor and capacitor combination in the feedback network. Okay, so that is LC. Here Hartley, Colpitts, different oscillators are there. Even these experiments also we have in the laboratory. Okay, and then crystal oscillator. So we will be using a piezoelectric crystal, its characteristics. So how it is able to produce 180-degree phase shift, and it is also acts as an oscillator. So this is very sensitive oscillator crystal. Okay, so that aspect also you'll be learning. So this is 3 they have in the syllabus. So this we will discuss in the next coming sections. Okay, so for today, so we'll begin with the phase shift oscillator in general. Then we'll consider the different amplifier based phase shift oscillator, nothing but OpAmp. Okay, then BJT, FET, like that. So all things you have studied, no? So like that we have different amplifier based oscillators. Okay, so first phase shift oscillator. Okay, this is a general block diagram. Okay, okay, so this is a amplifier block here. Okay, so this is the amplifier block, and for that, so you have given a feedback now. Okay, so the configuration can be written like that. It can be written in down or it can be written in front, wherever. Okay, but its output here, connection is important, right? So output is connected to the here, see here, input of, this is the section we call it as RC phase shift oscillator. Okay, so what you have here is the cascading of 3 R and C combination. Okay, so it is also scientifically proved that, okay, one RC section will give you at the output here 60-degree phase shift. Then here again it will produce 60-degree phase shift, and then again it will produce 60-degree phase shift, and all 3 are connected in cascade, so they will get added. Okay, 60, 60, 60, because you know that gains are multiplied whereas angles are get added. Okay, so 60, 60, 180-degree phase shift will come, and this amplifier is having minus showing because it is having a 180-degree phase shift. So together it is giving 360-degree, and it is satisfying the Bhatkal criteria, and it will act as an oscillator. And again, one note is that, so always don't consider that this all will give exactly 60-degree. No. Okay, so the first section may be giving little more compared to second one, because here resistor will act as the load. Okay, so it will dissipate some amount of heat, right? So then it will reduce little bit less than that, and this will produce little less than that, and overall at the output of this 3 section you will have the 180-degree. Okay, so that is the idea of this phase shift oscillator. Okay, so that only I will explain in next sentences. So just I'm reading out. Okay, look at the basic structure of the phase shift oscillator is shown in figure. It consists of a negative gain amplifier, okay, minus K, with a 3 section, or it is a third order RC ladder network we call, in the feedback. The circuit will oscillate at the frequency for which the phase shift of the RC network is 180-degree. Only at this frequency will the total phase shift around the loop is 360-degree or 0-degree. Okay, because this negative gain amplifier will give you 180-degree, and this feedback network will provide you 180-degree. Together it is giving 360-degree. Thus by it is satisfying the criteria of oscillation. Okay. Going to next slide. Here we should note that the reason for using a 3-section RC network is that there is minimum number of sections, okay, lowest order, that is capable of producing a 180-degree phase shift to at a finite frequency. Okay, so there may be question, right? So why it will be section of RC network, okay, and minimum how much? Okay, so it should be done. Okay, when you have connected single RC section, you may get 60 degree. So you can do this practically everything. You will not see the oscillations. Waveform will not come at all. So when you are doing oscillation circuits, no, so getting the sine wave is important. Okay, the output we call, right, in lab. So that will come only when it is having 3 RC sections. So when it meets that criteria of Barkhasan oscillation criteria. Okay, and for oscillations to be sustained, not only generating the waveform, you should sustain it, right, maintain it. The value of K should be equal to the inverse of the magnitude of the RC network transfer function at a frequency of oscillation. Why it is told inverse of magnitude of RC network? Because another criteria also should be satisfied. No, A into beta, right? Magnitude of A into beta is also equal to 1. The loop gain should be also equal to 1, and angle should be 360 degree or 0 degree, right? To satisfy this, if you have a gain K of the amplifier, then beta network gain should be 1 by K. So 1 by K, K will cancel out and it will give you 1. Okay, so that's what this sentence about. However, to ensure that oscillations start, the value of K has to be chosen slightly higher than the value that satisfies the unity loop gain condition. So initially you can keep it higher, A beta greater than 1 you can keep, and then when you sustain it to get the oscillation, you can tune it, okay, to get the oscillation. Okay, because in practically when we say exactly equal to 1, it will not happen, right? So even you have understood in the rectifier example, right? So theoretical value of your ripple factor or whatever measurement you have done, and practically when you have done, there is a little bit difference, right? So that will happen normally in the electronic circuits. Okay, that's possible. Oscillations will then grow in magnitude until limited by some nonlinear control mechanism. Okay, so this is about the phase shift oscillators, RC phase shift in general. Okay, so now what I'm going to do next is, in the place of amplifier, okay, instead of this minus K, this RC section will be there in all the oscillators because that is the feedback frequency selective network. Okay, whereas this amplifier part I will consider now different. So I will consider OpAmp. OpAmp we have not discussed yet. So we'll be discussing that in the coming sessions. Okay, the module 4 and 5 is about OpAmp. So that's why just I will show you how it looks like, OpAmp based oscillators. Then we can use FET also here, JFET, MOSFET, like that. We can use the BJT also. Okay, so in this we will be discussing FET and MOSFET, FET and BJT. We will do detail analysis. Okay, so what we need to find here is finally the frequency. What is the frequency of oscillations of the generated waveform? Okay, so for that you need to do derivation. What is the formula for BJT based phase shift oscillator? Okay, or FET based phase shift oscillator? Okay, so normally RC phase shift oscillator equation will come approximately same, a little bit changes. Okay, so that we try to do in the coming section. Okay, so this is the general phase shift oscillator. See here, the first variety of RC phase shift oscillator is OpAmp based phase shift oscillator. You know that OpAmp is a IC based amplifier, right? It will having number of MOSFETs, okay, so in its circuits. So it is indicated by the IC741. Okay, so it you maybe the Shrishail sir has shown you in while doing the basic electronics class. Okay, so those who have done it, okay, in the first semester level, IC741 we indicate that OpAmp. So it is be having the 8 ports. Okay, so it is having the supply everything like you have seen in the digital labs. Okay, for NAND gate, AND gate, like that. So you have seen there I think 8, right? So 16 pin ICs I think. Okay, so here it will be little less. Okay, so that is IC741 OpAmp. Using that we will form the amplifier. Okay, that is called as OpAmp based phase shift oscillator. So here this block indicates your amplifier. Okay, So this is the op-amp. So it is the non-inverting input and inverting input. These basic things you know in basic electronics. Okay. And here the power supply is there. So plus and minus, it is not shown here in general. Okay. And this is the output here. What you have to remember here is the output, and this output should be given as feedback to the inputs here. So feedback, what you have, 3 sections of RC here. Okay. So some cases 1 R may be missed. Okay. So are eliminated because it may reduce the 180-degree phase shift. Okay. So that's why compulsorily we should have 3 RC, no, because the output will have a amplifier. It may have internal resistance, okay, at the input. So because of that, the chances of load get added to that. Okay. So that's why. So here next section I have not taken R, meaning so it is having some internal resistance at the input here. So it will act as the load and it is satisfying that 3 sections of RC. Okay. So this is the op-amp based oscillator. So just we'll give the circuit explanation, that's it, and no analysis is there, equation derivation and all we don't have, because op-amp you are not started studying. Okay, that's why syllabus also they have not kept the equations, but FET and BJT will do that. Okay, so what is this other circuit here is the diodes and the 4 resistors we have. This is called as a limiter. Okay, so limiter circuit, something you may be come across or you may be coming across in future. So that is limiting. So about that I will explain in next slides. Okay, so this is a limiter circuit, you remember, that's it. Okay, and this is the RF. This is the normal op-amp configuration, right? Differentiator, integrator, you have seen some resistor in the new this is op-amp. So upside you will have some resistor or capacitor combination, like different adder, subtractor and all you have seen. Same way, this is the feedback resistor here, 100 kilo ohm along with 50 kilo ohm potentiometer is done together. It is acts as a RF, feedback resistor of the op-amp. So whereas this D1, D2 and the 4 resistors will form a limiter circuit, and this is the output here given as feedback to the RC sections here. Okay, so this is it. Okay, so about the circuit of op-amp based phase shift oscillator, we'll just explain you based on this. Okay, the figure C shows a practical phase shift oscillator with a feedback limiter. Okay, limiter circuit I told you, consisting of diodes D1 and D2 and resistors R1, R2, R3 and R4 for amplitude stabilization. Okay, so because in op-amp stabilization, amplitude stabilization is an issue, for that this circuit is used. To start oscillations here, RF has to be made slightly greater than the minimum required value. Okay, that is the feedback resistor in the op-amp. So for starting, okay, oscillations to start, this is the first criteria in the op-amp based oscillator. Although the circuit stabilizes more rapidly and provides sine waves with more stable amplitude, if RF is made much larger than this minimum, the price paid is an increased output distortion. Okay, so in the op-amp based oscillator, what will happen here is RF should be made slightly larger to get the oscillations. But when you make RF is more, so there is a chance of output distortion. Okay, so that is the limitation of using op-amp based phase shift oscillator. A practical RC phase shift oscillator can also be designed using BJT or FET amplifiers. Okay, so we have a junction FET and the BJT type amplifiers. So based on that also we can do the oscillator circuits. Okay, so this is about the introduction of oscillator, whatever we have discussed, and then we have discussed what is phase shift oscillator looks like, a general amplifier and a 3 RC sections. Then we have considered first op-amp based RC phase shift oscillator. Okay, so next is the important, that is FET based phase shift oscillator. Okay, so here we have the detailed analysis, everything will do whatever we have done in amplifier, AC, small signal AC analysis model, and then derivation, all these things is there with this. Okay, so time is less, but try to show you the circuit today at least, and tomorrow we'll continue the complete discussion. Okay, so what we are going to ask in exam here is, so derive the frequency of oscillations for a FET based phase shift oscillator, frequency based RC phase shift oscillator, like that they can ask question. So you have to start from here. Okay, the circuit will take we'll reduce the circuit to a final form and then we'll find the frequency. Oscillator means its output is oscillation. Oscillation means it will generate sine wave. Sine wave output, how you will measure? Something it's time or frequency you have to measure, right? So that frequency only will do it derivation. Okay, theoretical derivation will do. Practically also we can see the result of that. Okay. So figure next D, I have named it, shows an FET based phase shift oscillator. The circuit consists of an amplifier circuit, common source, whatever. Okay, FET based amplifier, and then a feedback network. Okay, the FET amplifier is self biased with a capacitor bypassed source resistor. So all these terms you know, and a drain resistor. Okay, the feedback network consists of 3 cascaded RC sections. This is same for all the RC phase shift oscillator, cascaded RC sections. So just I'm changing the oscillators here, and the oscillator also, amplifier also different configuration we have seen. Common source, common drain, common gate. In that we have told common source we will be using in MOSFET FET based oscillators. Okay, and in the case of BJT it is common emitter configuration. Okay, again in common source amplifier there are various configurations we called, right? Biasing circuits. Very first we have learned. Okay, what are those? So it may be voltage divider bias circuit or emitter bias circuits or self bias. Emitter bias is also given name self bias. Self bias means you will have a drain side resistor, you will have source side resistor, you will have. Okay, and gate side anyhow input, high input resistance RG will be there. Okay, so such type of configuration is called as self biased. Okay, so that we are using. Okay, so just look at the picture. So it is showing the oscillator circuit. So this kind of circuit diagram only you have to rig up in the lab and you have to get the output. Okay, so that only we are doing. So this is the JFET. Okay, junction FET. MOSFET is not there, junction FET they have considered. Okay, so the drain side RD is connected and the source side RS is connected. Okay, so sometimes input side resistor will be connected, not connected, because this resistor only will act as sometimes load here. Okay, so R is not written, I have, so in the notes you have to write down that. Okay, so this is RD. Okay, this is the amplifier, and at the source side you have the RS, and it is bypassed with the coupling bypass capacitor CS. Okay, and it is connected to ground, and this is the output now. Okay, so at the output side we have connected the feedback. This is given to feedback network now. So feedback network is having 3 cascaded RC sections. So this is one section, this is another section, and this is another section. And the output of this here you will have 180-degree phase shift, and this amplifier output will have 180-degree phase shift. Together it is satisfying the Bhatkal criteria of oscillation, and it is producing the oscillation. Okay, so this output of this is called as VF. Okay, the feedback voltage we call. So that we have shown there XF in the general block diagram. I shown you XF. So X is instead we'll take V here. The term is voltage here. That's why VF is denoted feedback voltage. Okay, so input voltage is denoted as VI. Okay, and VDG supply, all these things are there. Okay, this is the amplifier and this is the feedback network. This together we call it as oscillator circuit, and this is a FET based RC phase shift oscillator. Okay, so I will stop for here. So tomorrow I will do the detailed analysis of this. Okay,